Okay. Well, hold on to your seats because things are about to get a bit faster. If I'm gonna get to say anything about what I'm interested in. So I want to talk about the key theory of a specific ring. And we saw last time, 5 minutes ago, that that Quillen computed the K theory of finite fields entirely. And I think it's safe to say that those are the only rings whose full K groups, all of whose K groups are known. So it was a question already from the early 1970s. 1970s. So compute the K groups of Z mod P to the n, rings like Z mod P to the n. And turns out to be really hard. So what was known before, previous work, got up to, well, here for n at least 2, right? N equals 1, that's Z mod P, that's a finite field, so that's covered by Quillen's theorem. So here we're interested in Z mod 4, Z mod 8, etc. So previous work got to K 2P minus 2, or of Z mod P to the n, i.e. they computed Ki Z mod P to the n for 0 less than or equal to I less than or equal to 2P minus 2. What's the first open case that leaves? Well, that already leaves open. So what about K3 of Z mod 4? So until the work that I'm about to describe, this was open. And it's about as low as you can get. And really what we do is we provide an algorithm and we give an implementation of that algorithm, which computes the K groups of Z mod. It computes any given K group of any ring like Z mod P to the n, given enough time. Okay, so let me make a couple remarks. So first of all, Adorami Cuckoo already proved, I forget when, that that Ki of a finite ring R is finite for I at least 1. Namely, if I have a commutative ring or even associative ring, which is actually just finite as a set, then each of its K groups is also finite. It's a finite abelian group. Okay, so what our aim here is to compute some finite abelian groups. So you would hope that this is something that we can do. Okay. Okay. So what are some other kind of easy reductions? So Gabor rigidity says that well, it's more general, but it says that K theory of Z mod P to the n, if I do it with ZL coefficients, is the same as the K theory of FP with Z mod L coefficients for L not a prime not equal to P. So what does this say? What I'm saying is that if I ignore the residue characteristic P, the L-adic K theory of Z mod P to the n is the same as the L-adic K theory of FP. And so this was computed by Quillen. And all it's doing is picking out the L primary torsion groups from Quillen's calculation. Okay. So what does that leave us? So we're left with, if we want to compute the K theory of Z mod P to the n, we're left with K theory of Z mod P to the n with p-adic coefficients, i.e. just the p-torsion information in each of its k groups. That's what we want to compute. Okay? So that's the open problem. And now there's a major theorem of Dundas, Goodwillie, and McCarthy, which is one of the main results in the subject. And it lets us do a sort of devisage with rings. So it says if we want to measure the difference between k theory of z mod p to the n, and I'm going to sort of redundantly put with z mod p with p-adic coefficients. So I p complete everything, and I want to compare it to the k theory of fp, which we know by Quillen. Then there's something I can do. I can take this trace map. I can map to the TC of fp, and I can map to the TC of z mod p to the n. And this is a pullback square. It's a pullback square. Okay. What I'm saying is that there's a mystery, there's a new player called TC, which is topological cyclic homology. My understanding is that the previous instantiation of this seminar had quite a bit of information on TC. I'm not going to tell you too much about what it is, but if it's an invariant of rings, and I'm going to tell you a little bit about how to compute it in a moment, but I'm not going to tell you how it's defined. But the point is that this is a pullback square, which means that on homotopy, there's a Meyer-Vietoris sequence. Like pi I of this maps to pi I of this plus pi I of this. That sum maps to pi I of this, and then there's a boundary map to pi I minus 1. Okay. But what that means is if you know these three terms, then you know this term. Okay. So that gives you a strategy for computing k theory of z mod p to the n by trying to compute these three terms. Well, in this case, it's particularly easy because, in fact, these two terms have pi I is 0 for I at I more than 0. So this side is a computation of Quillen, and this side, I guess, is probably a computation of Hesselholt and Madsen. Sorry. And so that implies, what does that imply? That implies that ki of z mod p to the n, if I throw out all of the prime to p information, is isomorphic to tci of z mod p to the n. Okay. So that probably, you might think that doesn't help you a lot because, what is TC? I haven't told you. There's no suggestion yet that it's any simpler. But let me give a little bit of taste of what TC can do for you. Okay, any questions before I realize I might be going faster and faster here? But. So I'm not going to tell you what TC is, but I'm going to tell you that TC has a motivic spectral sequence. And that motivic spectral sequence has an E2 page called symptomic cohomology. And I'm not really going to tell you what symptomic cohomology is in general either, but I'll give an example of what it is in one case that's relevant to us. Okay, so part B here is symptomic cohomology. And I'll just write some symbols down. And right, let me just write some symbols down. So for R, some kind of reasonable ring, reasonable p-complete ring. Remember, we're in the business now of computing p-adic k-theory, and the hardest case is sort of when p is, or maybe the main case is when p is not invertible. P, we take a P-complete ring that's reasonable in some sense. Then there's complexes ZP of I of R. So this is an object in the derived category, the P-complete derived category. Okay, so it's a complex, or it's represented by a complex. And what is it? I will give you the definition and introduce some more symbols. So you take the absolute prismatic cohomology of R. You Nygaard complete it. You Broglie-Kissen twist it. And you take part of the Nygaard filtration. And then this has a map to the same thing, but without the Nygaard filtration. Okay. And there's two maps from the left to the right called can and phi. And you take the fiber of those. This, if you were at the talk last time, this should be analogous to this is analogous to the fiber sequence TC of R, TC minus R, and TP of R. But if that doesn't mean anything to you, ignore it. The point is there's some theory called prismatic cohomology. You've probably heard of it. I'm going to explain a little bit how to compute it in the specific cases that we care about. And there's prismatic cohomology has a filtration, the Nygaard filtration, and we want to complete that filtration. It doesn't start out life complete. So we formally complete with respect to that filtration. And there's also this curly braces I. That denotes the what's called a Broglie-Kissen twist. And what you should think of that as being a p-adic analog of the Tate twist in a Tull cohomology. Okay, so these are just symbols, but I'll tell you some things about these symbols later. The important theorem here is, due to the second paper of Bott-Morrow and Schulze, is that there's a spectral sequence which looks an awful lot like the Atiyah-Hertzberg spectral sequence. It goes from the degree S minus T cohomology of the minus T symptomic complex, and it converges to TC minus S minus T of the ring R. So what that means is if you can compute all of this, then you're pretty happy. Let me mention another theorem due to myself, Akil Matthew, Matthew Morrow, and Thomas Nikolaus, which computes, which shows that there's a big vanishing for these complexes. This is 0, for S more than T plus 1. And also less than 0. So it really is like a coaching, it's like a cohomology theory. There's no negative cohomology. But it also vanishes uniformly in any dimension for a fixed weight in high enough degrees. And so that lets you kind of draw a picture of this spectral sequence. Sorry, I already messed up. I won't draw at all. So each row is the cohomology of some specific weight. And then the stuff contributing to a given degree are these diagonals. So anti-diagonals. Let's get a different color. So this is TC0, this is TC1, this is TC -1, and so forth. And the differentials, how do they look? There's room for one differential. This is a D2 differential. And one of the sort of points one of the upshots of our calculation. So right, this keeps getting bigger and bigger. One of the points of our calculation is to leverage the fact that you can prove that for Z mod P to the N, only everything outside of this region is 0. Well, okay, sorry, it's not like it stops here. Everything outside of this is 0 for Z mod P to the N. Okay, in particular, all this forces see all of the differentials either start or end with something which is 0. Okay, so spectral sequence collapses at E2. In particular, what that tells us is the following. It tells us that K so K2I -1 of Z mod P to the N with p-adic coefficients is isomorphic to H1 of this symptomic complex. And K2I -2, so this is for I at least 1, or yeah. And this is for I at least 2, is isomorphic to H2. So in fact, for these particular rings, there's no H0 either. Okay. And so we've reduced the computation of K theory to the computation of the cohomology of these symptomic complexes associated to Z mod P to the N. And so let me now talk about how to first, let me give a kind of soft, what I call a sort of soft argument. For that. Oh yeah, actually, I was going to give a related example first, which kind of helps to figure out what's going on. Example, so here's a related example, which is very well studied. Let's, instead of taking Z mod P to the N, let's take FP adjoin a polynomial variable Z modulo Z to the N. So this is a ring with the same order as this ring. It's also like nilpotent. It's also has lots of nilpotent elements. So they kind of have very similar behavior, but the K theory of this ring has been computed for a long time ago by Hesselholt-Madsen, and more recently using newer, more sophisticated techniques by Spears, Akil Matthew, and Yuri Salima. And basically it's easier because it's purely in characteristic P. And so you could sort of use methods from crystalline cohomology instead of from prismatic cohomology, and crystalline cohomology has been well understood for much longer. And let me just mention the result of the argument in this case, which is first of all that K2I -2 of Z of this ring with p-adic coefficients is 0 for all I at least 2. So all of the even cohomology, all of the even K groups vanish, and K2I -1 are ZP. Well, it's isomorphic to some specific group. It's isomorphic to the big Witt vectors of FP. modulo some Verschiebung. So this is a little bit, sorry, the length IN. So here I have this I is the weight, and this N is the power here, mod the nth Verschiebung of the Witt vectors of length I. Okay. But note, this is weird. This is like the big Witt vectors and not the p-typical ones. But my point just being that one way to actually compute this is to just compute, in this case, that this is H1 of ZP I of this ring R. And this computation then has been recently done by direct methods by Akil Matthew and Yuri Salima. So it somehow really already was known that, at least in some cases, you could make calculations like what we do. Okay, so that's that. Now, one of the key ideas in, well, at least how we're writing this up, maybe not how we originally came up with a proof, is what I call crystalline degeneration. Which we want to compute the symptomic cohomology now of these rings Z mod P to the N. And we don't know how to do it, but we can make some coarse observations about how it must look like by comparing to what happens when we do this crystalline degeneration. So here's what I mean by that. I mean, on here, I have Z mod P to the N has the p-adic filtration. Right? Just given by, I have Z mod P to the N, I have the ideal P, I have the ideal P squared. And eventually I get 0 at some point. And so for any filtered ring like this, there's an additional filtration on the symptomic cohomology. So this filtration leads to a filtration I'll call F star on the symptomic cohomology. And so what I'm saying is, like, the symptomic cohomology of a filtered ring is filtered. Okay, so that's something one can prove. And the crucial point of that is that now the associated graded of this filtration, we still don't know what it is, but it's the same as the associated graded of the corresponding filtration of the associated graded ring. Well, this associated graded ring, what is the associated graded ring of this p-adic filtration? This is Fp adjoins Z mod Z to the N. And what I've just told you is that this is known, the symptomic cohomology of this is known. And in particular, it's finitely generated, and one can figure out that in high filtration weights, everything goes away. So specifically, what you can figure out is that ZPI of Z mod P to the N, it's actually equivalent to just the filtration part going from 1 to IN minus 1. Okay. And this is, you do by looking at this and just checking in the computation of the symptomic cohomology of this done by Yuri Salima that there's nothing in high graded pieces. And so you just get to stop somewhere. And this observation is somehow a key component of what lets us compute this, like, by computer. It lets us stop at some point. It lets us, the fact that we have this upper bound means that we get to do some work at finite level and then know that we've actually computed everything. Okay, so this kind of observation is really crucial. Okay, so just let's remember that, because what that, right. Okay. So that's one really crucial idea. One really crucial idea. That's kind of fun. So how are we going to leverage this? Well, remember, right, so let me start a new section here called prismatic envelopes. So remember I said that this ZPI of any reasonable ring R is given as the fiber of two other maps. I'm just repeating myself, but it's okay. So it turns out that this all passes to the filtration. So I can kind of write down F1 through IN minus 1 here, F1 through IN minus 1 here, and now you start to get a headache because there's two filtrations in the picture. There's one here. Okay, so the first observation is that, yeah, the same filtration trick means that there's a filtration on these prismatic cohomology terms. And that's good because while the symptomic cohomology is finitely generated, the prismatic cohomology itself is absolutely not finitely generated. So somehow our strategy can't be, if we're going to use a computer, to somehow actually compute, we can't actually compute this whole term and this whole term directly and just take the fiber, that they're infinitely generated abelian groups, right? So it's just not plausible. But the fact that we're able to get this finite filtration there means that we can compute that up to in a finite range and this in a finite range. Okay. And that it turns out we are able to do, and I'll explain how we're able to do that right now. Okay. So what's the basic idea? Maybe these two things should have been in a different order. So what's the basic idea now? So it's what I'll call Liu-Wang descent. Although perhaps one might also call it Breuil-Kissin descent, but I'm not sure there's a standard name for this. And this is really the key idea that makes everything work. See, I've told you we have to compute some prismatic cohomology, and you might reasonably ask, how the hell are we going to do that? And there's no real general way of doing that, at least at the level of granularity that we're going to need in order to make some actual calculations. So there's an idea which has its origin really in this paper of Liu and Wang on topological cyclic homology of local fields, and also in work of my co-authors Achim Krause and Thomas Nikolaus from a slightly different perspective. They turn out to kind of give equivalent approaches, but the Liu Wang one is the one that seems to work a little bit better algorithmically for us. So what is it? Right. What is it? So I'm going to say this without saying something really topological. Well, okay. So where's my big diagram? Okay. For real, where is it? Okay, well, okay. So Okay, so here's the basic idea. We're interested in understanding TC of our ring R. And TC is really a functor on cyclotomic spectra. And so what we're really applying it to is THHR. And THHR is really, you should think of this as being the Hochschild homology of R, not relative to the integers, but relative to the sphere spectrum. And so the basic idea of this Roy-Kissin descent or this Liu-Wang descent is to do the following. In the case that I'm interested in, Z mod P to the N, I have the unit map from the sphere spectrum, but I also have this map from S, a polynomial ring over the sphere spectrum, which sends Z to P. And so I can also consider THH of Z mod P to the N over S adjoins Z. And there's a map from THH to here. And what I can do is I can take the bar construction or Adams resolution or check complex or whatever you want to call it, and take iterated tensor products and then take tote of some big cosimplicial diagram. So the next term will be like THH of Z mod P to the N over S adjoins Z in two variables now, where both variables map to P. And it turns out that this map to the tote is an equivalence. That's the one of the main tools, main observations of Liu and Wang to compute TC of local fields, and it is also what we use. And it also becomes equivalence when taking TC. So TC of Z mod P to the N. Some tote of relative TCs. And it turns out that there's also a theory of relative prismatic cohomology and relative symptomic cohomology. And so what that lets us do is realize ZPI in any given weight of Z mod P to the N as being tote of some big diagram, cosimplicial diagram, ZPI, Z mod P to the N over. Now we're not really over the sphere, but we're over a ring, which I'll write ZP, its power series in one variable. That's the first term. Sorry, I'm getting a little small. And now power series in two variables. And then this continues. Okay. And remember that this sits into a fiber sequence. And this, let me just call it R for simplicity. Where this is the absolute prismatic cohomology. And now this, we can sort of just extend this diagram. There's a cosimplicial fiber sequences. And now you have this relative, this relative prismatic cohomology here, and more than or equal to I R over ZP adjoins Z. And now there's a little bit of a twist, namely a Frobenius twist, which, well, okay. Which, let me see my perspective on this. So these are fiber sequences in each cosimplicial degree, and then they, in the limit, they become this fiber sequence. And what the overall structure of the proof now is to the construction of our algorithm and so forth. Well, I already told you, so you can check using crystalline degeneration, the location of the cohomology, the symptomic cohomology. So we know, let me just scroll up for a second and I'll come right back down. Right, I told you we only have these 2 degrees to worry about, just H1 and H2. So it only, for weight at least 1, there's only degree 1 and 2 cohomology. So the first observation then means that, oh, and then here, okay, so let me make remarks. So remarks, H M N Z P I R equals 0 for n not equal to 1 or 2. For I at least 1 and n not. Okay. So that's point 1 for the rings we care about, for all, the Z mod P to the n. But then the other point is that these terms all turn out to be discrete. I.e., in principle, these are some cohomologies, so they're in the derived category. But in fact, everything in this diagram turns out to be discrete. And so what it turns out that means is that you can get away with just computing the first 2 columns and then computing here. So somehow there's a cohomological dimension argument, which if you have done some stuff with Hopf algebroids in the context of chromatic homotopy theory might be familiar. But there's a Hopf algebroid argument that says that basically we can just reduce to the first couple terms of this. So just this part of the diagram. And that's nice and finite. Okay, so that means we don't have to go out completing higher and higher cosimplicial degrees. So that's really crucial. We can also put the filtrations everywhere. And and again, then we don't have to worry about crazy high cosimplicial degrees or crazy high filtration level. So what I'm trying to say is to convince you that there should be some finiteness in the picture that might make this look algorithmic. And let me say, right, okay. So what to say now? So okay, so what we then oh right, I guess I wanted to tell you something about prismatic envelopes. So what is this prismatic envelope? So let me tell you what a couple of these things are. So let's consider the case of prism R over ZPZ, where Z maps to P. So it turns out that this has a very nice description. So it's actually, despite being defined as the cohomology of some site, it turns out to be discrete, a discrete commutative ring. And it's isomorphic to the following. It's ZP power series C, power series Z, and then a certain universal construction, which is Z to the N over Z plus P. And then I have to PZ complete the result. What is this universal construction here? So I haven't really talked much about it, but behind this prismatic cohomology theory is the theory of delta rings. So there's also prisms, but somehow what matters at this point is just delta rings. And this is just a universal delta ring construction. So if we ignore this completion, this is the following. It's you take you take the free delta ring on an element X. A delta ring is a ring with a lift of Frobenius. And that's an algebraic theory. So there's a notion of a free one. A free one turns out to be, okay. Let me just make an aside. That was a very bad. Let me just make an aside that this is just a polynomial ring on symbols X, delta 1X, delta 2X, and so forth. So it's literally just a polynomial ring in countably many generators as a ring. There's some extra structure, but that does not matter for what I'm about to say. So I take this and I mod out by a certain relation. I mod out by a relation that I want to say that z to the n should be equal to x times z plus p. So you see what this symbol is saying is I want to say I'm forcing z to the n to be divisible by z plus p. That's what this relation says. But not just anywhere. I want to take this and I want to close it up under this delta operation. So if you like, in this, if you want to think of delta rings as being rings with lifts of Frobenius, this ideal is not closed under hitting it with Frobenius. So I just close it up. I just keep hitting it with Frobenius and take all of the elements that hits and take the ideal generated by all of those. Okay, so and then I PZ complete it. Well, that's great. And if you wanted to try to like work with this with pure thought, you might get a little discouraged. But this is a pure algebra construction. So I think you should be convinced that like, if you had to, you could put this in, you could make a computer package which encoded something like delta rings and could do this kind of construction, at least with as long as you only had finitely many of these terms in the picture. And so that's part of what we did. Okay, so we made some computer package where we could work with those kind of objects. And what that does is that computes for us this prismatic cohomology. And so in the couple minutes remaining, let me not say too much more about the details. The upshot is you can compute these up to finite filtration and write down a cochain complex representative for this, as in an actual matrix, like, you know, actual finitely generated abelian groups and a matrix. Okay. So specifically, what we prove is we construct a specific representative. This lives just in the derived category, but we construct a specific cochain representative, cochain complex representative that looks as follows. And then this is just some matrix, and this is some other matrix. And so the algorithm is about filling in the entries of these matrices using this theory of prismatic cohomology and analysis of these prismatic envelopes. Once you've filled that in, then you can use Smith normal form to compute the cohomology of this complex. And that's how the calculation goes. So I didn't get very far into talking about V1. Let me take the last minute and say one word about V1. So first of all, I'm going to let FPI of a ring R, that's just going to be ZPI of R mod P, the cofiber of multiplication by P. And it's basically there's a special element VP1 in the weight P minus 1 mod P symptomic cohomology of ZP. And this V1 is super important. It's related to the V1 that comes up in chromatic homotopy theory. So if you know what that is, great. If you don't, that's okay. And it was known before us, thanks to work of Clausen, Bott, Matthew, and also Lond, Matthew, Meyer-Tama, that so this element acts on TC. Well, it basically acts on the K theory of Z mod P to the N, but now mod P. So we take the cofiber of multiplication by P, and V1 acts nilpotently. And this is a very important result that goes into a lot of important mathematics. So, for example, it's used to prove that the K1 localization of the K theory of R agrees with the K1 localization of the K theory of R 1 over P. Which is, if you know what those words mean, great. If not, that's okay. But let me say, by contrast, what happens away, like, right? If you did something else, if you did like KU, sorry, not KU. If you did like the algebraic K theory of the complex numbers, mod P, then this also has a V1 acting on it. And if you invert V1, you actually get a periodic K theory spectrum modulo P. So this is the spectrum which has FP in each even homotopy groups and 0 elsewhere. So in this case, you're as far from being nilpotent as possible. But let me just state my theorem and be done with that. So we already knew that the action of V1 is nilpotence, but kind of an amazing fact, using the explicit nature of our algorithm, we were able to actually compute the exact order of nilpotence. So specifically, V1 to the P analog of N is 0 on KZ mod P to the N mod P, and no smaller power is 0. Oh yeah, well, okay, sorry. Maybe just for safety, let me say twice this. Okay, gosh. Okay, let me keep an exact statement. I don't want to say K theory of Z mod P to the N. I want to say on the associated, on the direct sum of the symptomic cohomology. But of course, I mean FP coefficient. So like, you can get a result for K theory too, and in particular, reprove this theorem, but with an explicit bound on the degree of nilpotency. But we don't know the exact correct answer there. And what is this weird number, this N analog of P? This is P to the N minus 1 over P minus 1, also known as 1 plus P plus up to P to the N minus 1. Why is it called a P analog of N? Well, if you set P to be 1, you get the number N. And so the theorem is that exactly this power is what you need to get the 0 operator, and no smaller will do on the associated graded. And I'd probably better stop there. So thanks for listening.